Hey everybody, it's Taylor Sparks here again, and I'm back from vacation with another video on Materials Informatics. Today we're talking about materials data repositories. And that's important because if you're going to be doing machine learning, you got to get your data from somewhere. So where are you going to get your data from? Let's talk about that. First, before I talk about that, let me set the stage by talking about this really cool store in my hometown. In Ogden, Utah, you've got this store called Smith & Edwards, the country boy store, and their slogan written giant on the side of their store is, "We have anything you want if we can find it." And the whole idea behind the store is that they've got everything there. You don't have to go to multiple places. They've got it all for gardening, for hunting, for you name it. It's all in one place. They've got these giant tanks with silos and missiles on top, and out back, sure enough, they've got anything. It's mostly surplus, but man, one place. How great is that? If you could go to one place and get everything. Now, contrast that with when I was in grad school living in Santa Barbara. Down Main Street of Santa Barbara, if anybody's been there, you know that it's made up of a bunch of little boutiques. Most of them are tiny little stores offering some super niche little thing. I remember there was a store, a whole store dedicated to clothing for dogs. No joke. That was a thing that was there. So on Main Street, you could sort of find anything you wanted in Santa Barbara. Or at this one store at Smith & Edwards, you can find anything you wanted. The question is, when it comes to materials data, is it centralized or dispersed? Is there one place where we can go to get all the materials data that we're really going to need for materials informatics? Or is it dispersed and you're going to get little bits and pieces everywhere? So unfortunately, right now, it is dispersed. There isn't one great repository. There's no Smith & Edwards for materials data yet. Things are moving that way maybe, but right now there's not really that. So what I'm going to show you in today's video is this sort of constellation of these federated databases, some of them not so federated, and just show you what the landscape looks like for materials data right now. So let's go ahead and jump over to the internet and start by looking at these. So I'm going to start with a bad example, and then I'm going to show you a bunch of great examples. So this one is the Topological Materials Database. Pretty cool website in what it can do, right? So you can punch in different compounds, right? So we could punch in like vanadium, bismuth, telluride, or whatever, right? And if there's nothing there, it'll tell you nothing's there. You can come over here, and you can actually punch in things, you know, titanium, borite, or whatever else. And it will tell you all the things that it has in the database to match this. So it says there's 4 TIs, 13 SMs, and 3 trivials. So this is a focus on topological materials. That's what these different abbreviations, topological insulators, for example. And it'll give you information on them. You can actually pull it up and you can see them. So it's a cool website. It's slick. It looks really good. The downside to this is that this data is not accessible. In Materials Informatics, well, and in the broader Materials Genome Initiative, we have this concept of FAIR data. FAIR data, F-A-I-R, is an acronym for findable, accessible, interoperable, and reusable. If you want your data to comply with Materials Genome, it needs to be findable, meaning you have to be able to find it, search for it. It needs to be discoverable. Accessible, so you have to be able to access it, and that's the problem with this one, is that you can't actually access the data. You can just see little snippets of it. It needs to be interoperable, meaning it's not just made for one sort of data ecosystem. It needs to be able to work across, platforms and software and all that. And then reusable, right? So this one falls short of that because it has some really cool things, but you can't extract this data. There's no what's called API, and in our next video we'll walk through an example of using an API. And if you email these people and ask for the data, they say no thanks, which is a bummer. So hopefully they'll change that practice. But you know what? Not that long ago, I was in the same boat as them, right? Way back 10 years ago when I was first getting into this field, we did the same thing. You know what? We were grabbing data from literature, which is what these folks did. They grabbed data from many, many papers. We did the same thing. I hired undergraduates way back then, and you would snip an article from a paper. So let's say this was a figure from a paper. So this was the figure that we were interested in. You'd take it to somewhere like Data Thief or Webplot Digitizer. This is what you see here is Webplot Digitizer, where you can actually put different points on your axes, right? Point 1, point 2, point 3, point 4. So let's go ahead and do this. And then you can calibrate your axes. So I'd put a point right here, and you can move it to be exactly where you want it to. Maybe I'd put a point over here and get it where I want it to, right? And then I'd put a point for my y-axis, put it right there, and put a point for my y-axis up here. And once you've done that, now you can tell it where those are at. So you can say on the x-axis it starts at 1 and it goes up to, looks like 1e to the 4. and that is a log scale. And on the y-axis, it starts at 10, and it goes up to 1e to the 3, it looks like, and that's also on a log scale. And once you've done that, check it out. I can hover over this, and in the top right-hand corner over here, you see these numbers here, there, and there. That's what you're reading for these points. And so you can manually add data points. And believe it or not, this is what we did back in the day. We had undergrads just clicking on these things, bam, bam, adding data points. And also you can see, like, look at that. When I zoom in on, look in this window over here, you see when you zoom in that I'm not getting those points exactly right. They're sort of off. So then you'd have to correct it. You have to move it over. Oh, it's this headache. And even when you use like the automatic extraction tool, which is cool, let's go ahead and automatically extract this color. Any data point with this color, it's going to try and extract it. So you can run this. And you see that, oh, it messed up. It actually grabbed a bunch of other colors that weren't quite right. Now, this is a great tool. I still use WebPlot Digitizer all the time, but this would be a terrible thing to rely on to getting all of our data. But in the early days, that's what you had. You had literature where people were publishing data, and you said to yourself, I'm going to grab that data however I can. And software like this actually made it a lot easier, but it was far cry from perfect. Using that approach, we were able to build things like the Energy Materials database back when I was a postdoc at UCSB. Really cool database, right? When I look at it, you take a look at this thing, it generates all these. First off, you can pick lots of different things for your X and Y parameters. So on the X-axis, you can plot whatever you want here. On the Y-axis, you can plot all sorts of different things, some related to performance, some related to availability of the data, like HHI or scarcity, right? You can make it the marker size scale with different things. You can sort the data in different ways. Pretty rad thing. You can hover over this, and there's all the data. You can click on it, it takes you to the article. It's a cool way to visualize data, but we made the same mistakes that the quantum, topological quantum materials database was doing, in that we didn't make it available. There's no API, because back then I didn't even know what an API was. So we need to do better. And fortunately, over time, we've gotten better. And I'll show you some of our recent work where actually the data is made available, because this was for thermoelectrics. We did the same thing for batteries and some other materials. And we're going to make these data sets available in the very near future. So when it comes to actually finding good data that you can access, right? Not just find, but actually access the data and then reuse it, where do you turn? Well, fortunately, some great people out there have already done some of the hard work for us. Ben is a great guy. He's at the Materials Data Facility, Ben Blazik, and he has on his GitHub page here this called Materials Databases. So github.com, Blazik, B-L-A-I-S-Z-I-K, Materials Database. I'm going to put all these, by the way, in the show notes, in the YouTube description below. But he's already done a great job of going through and saying, hey, there's a bunch of materials-related databases out there, and I'm going to show you what the name is with a link to it, talk briefly about it, mention if it has an API or not, talk a little bit about the size of it, and it's really great. So he talks about, it's got ChemSpider, CCD, it's got AFLOW, OQMD, on and on. I'm going to show you a couple of these in a moment, but this is a really great place to start. So if you're not sure, like, hey, is there a database for, whatever, you might start with one of these lists of lists, right? That sort of lists all the databases out there, and then you can maybe Control F through this and look for whatever it is you're looking for, thermodynamic databases or whatever, right? Pretty cool thing. I think it's great. It also has some tools that are useful. He mentioned some code and some tools, some other platforms that you can use, cloud services, for example, Citrination, Globus, which is the Materials Data Facility, Figshare, which I've used, GitHub, obviously, a lot of cool things. So this is a great place to start. And then even this other one, like the sort of really small niche databases, like the ones I showed you in the beginning, he's got a lot of them listed here, which is pretty rad. So start with your lists of lists. And this isn't the only one, right? There's another one. This one's by Evgeny Blukin in Munich. Another great list, right? Lists a whole bunch of different things. First, he starts with some of the software and products. Then he actually gets to the machine-readable materials datasets, which is what you want. You want to be able to access it via code, right? A whole bunch of things are listed here and are definitely worth going through. I'm going to show you some of these that I find interesting from this. Okay, so that's another one. And then you've got another one from this fellow who I don't know, but another good list of databases. So I would start by going through one of these lists of lists when it comes to trying to find the data that you're interested in, right? And I'm going to include links to these three. Now, that said, all three of these lists all start, or highlight prominently the DFT databases. DFT databases are huge. We're going to start with OQMD. OQMD is pretty rad. This is from Wolverton's group at Northwestern. Very, very cool. It started for the Open Quantum Materials database, but they don't just do quantum materials. I think it's grown from what it was originally named. It now is just a very large inorganic database. It has lots of stuff. Phase diagrams, you can visualize structures. One of the cool things I like about this is you can actually tweet at it. Here's an example from the sort of documentation where you can tweet at the OQMD. You can ask for a phase diagram and tell it the elements, and it will spit back a phase diagram, which is so cool. It will tell you what things are stable. You can do really cool things with the OQMD. We've used it quite a bit in the past. So this is a really good one. Now, this is based off of DFT data. So if you come here to OQMD and you search for some things, right? So you're searching for whatever. Let's punch in an example. Let's do titanium nitride, right? If you search for it, what it's going to give you is calculations based off of density functional theory, right? So this is not experimental data. This is calculated, right? Sure enough, by punching that in, out comes lots of information that they can calculate. So they've got compositions. Looks like they've got the convex hull for this going between nitrogen and titanium. They show you the convex hull. So you've got all these metastable compounds that aren't the lowest energy, and then you've got the ones that are the lowest energy indicated. So tons of really cool information. On any of these, you can click on them and get more information, the structure associated with it, the formation energies, lots of the standard stuff that's present with DFT. So that is OQMD, right? Really great tool. Then you've got AFLOW. So this is led by, I think it's Curtarolo's group is the leader. I could be wrong. And this is another confederation. It's a bunch of different people. They have different schools that are involved. I think they show all the different people that are involved in it. There's a bunch of them, and they have lots of different tools associated with this. But it's similar. You can start by punching in something. So let's punch in a compound. Let's put in, let's do the same thing. Titanium, and we'll do the ampersand and nitrogen. Let's see what it comes up. So for titanium and nitrogen, it's going to go ahead and tell you all the things that it's got for it. So here's all these compounds that contain nitrogen and titanium, right? And among other things. So you can search for these, and the same things. As you click on these, you'll notice that it contains loads of information that can be calculated via DFT. So this is things like band gap, formation energy, thermal expansion, bulk modulus. Lots of those things can be calculated pretty easily. Not every property can be easily calculated, though. There's 6 or 7 that can be calculated pretty easily by DFT, and others not so much. So it's got the ones that can be calculated easily. Lots of information about the structure, the relaxed structure. Pretty useful stuff. Okay, so this is AFLOW. Then you come to Materials Project, which is very similar. You have to sign in. We go ahead and sign into the Materials Project. This is by Kristen Persson and Gerbrand Cedar over at Lawrence Berkeley National Lab. And much like you saw with AFLOW and OQMD, Materials Project is much the same way. You've got a periodic table. You can search for things by selecting elements, right? So you could select cobalt and carbon and boron and see what comes up, right? And it will tell you anything that they have from DFT calculations. If there's nothing, it'll say there's nothing, right? But otherwise, if you select it, it will have the stuff that you care about, right? So let's put something better. Let's put cobalt and nickel. Put an intermetallic. They should have something there. And sure enough, anything that's been calculated there, you can click on one of these, and you'll see much the same thing that you saw with OQMD and AFLOW, which is, energy above the hull, the formation energy per atom. They've got information on magnetic moment. They've got the structure, of course. Here they have the band diagrams, so the band structure and the density of states, which is really useful, really cool stuff. They simulate the XRD pattern. Here they, for not all their materials do they have the elastic constants, but they have a really cool tool where you can ask for it to predict it using statistical learning-based predictions. Read Materials Informatics. So they have a built-in tool where in real time it will, Materials Informatics, so using machine learning, will make a prediction of its elasticity. And also it says, hey, by the way, when you check that button on the right, you're voting for us to do the actual DFT calculation, which is going to be more accurate than the machine learning prediction. So really, really cool thing. Materials Project is one of the leaders in this area, in my opinion. We certainly use their stuff quite a bit. Great resource, and it has an API, so you can access it via code, right? So that's Materials Project, very cool resource as well. Let's keep going. So in addition to the DFT databases, there's other really good repositories, and some of these contain non-DFT, non-calculated, but actual experimental data. For example, NIST, if you go to materialsdata.nist.gov, they have this really great repository of different data sets. You can search by author, by subject, by year, right? So for example, let's say we want to go to a database on material science, okay? You can search through there and you're going to see all these things come up that have data associated with material science. You can click on these and it's going to have the links to the actual data itself, usually to the article. They have unique, URIs, so you can actually refer back to them and you can get the data. So NIST has been certainly leading, I think, the charge from the government perspective on the Materials Genome Initiative. They've done some amazing things to help form these, confederated data sets and getting them available to us. So this is one of those resources. Okay. Then you've got places like the Materials Data Facility out of CHIMAD, and I think it's the University of Chicago. They do some rad stuff. This is as close as I'm aware of anything to the Smith and Edwards model of all the data in one place. They have the potential to grow this into something where this could be where all of the data goes. I don't know if it's going to happen. There's other people competing. For example, Citrine has Citrination, and they, at least early on, wanted to be the leader to put all of your data. This was a private company. But both of these had the goal of being like the place to put your data. And I don't think either has fulfilled that mission yet, but there seems to be interest from both of them in doing that. Maybe less so in Citrination nowadays. But same things, you can discover data, right? You can browse for published data. You can search through the stuff. So you could say, I want experimental data. You could put in keywords up here. You could say, strength, and see what comes up, right? And sure enough, it's going to look through all the data that has available, and it's going to pull up whatever it's got, right? And sure enough, to say with strength, and if you want experimental data on strength, here's a couple that you could look at. When you click on them, eventually it's going to take you to a link to their Globus website, which is this cloud server that holds all this data for them. So you could go here, you could actually access the data. They have Python toolkits and libraries that make this really easy. So you can just pip install this and do some really cool stuff to grab this data. So that's a pretty great resource. Citrine has a pretty great resource. Again, you can put the same thing. You could go for properties. You could go thermal expansion, right? And if they have anything on thermal expansion, up it'll pop, right? And sure enough, you got this compound here, and it lists the thermal expansion. You can grab this data. You can actually download data sets. I think they put some limits on the size and the amounts that you can grab. I don't know if they've changed that since. I know that used to be the case, but Citrine is a very cool company. That they're the one that dragged me into this space, so I'm grateful to them, and they've done some cool stuff. Okay. Then you've got places like NanoHub. Now, NanoHub, I think, is less about the raw data and more about content related to Materials Informatics. So you'll find tutorials there. For example, this is welcome to the tutorial series for using the Material Simulation Toolkit for Machine Learning, MassML, right? You'll find with this some case studies. They will have some data and some packages and some code tutorials. So NanoHub's one that you ought to probably be aware of. And then you've got sort of like one-offs, and we've published a lot of these, right? So there's really great articles and journals out there that publish data sets, right? So this is in the journal Integrating Materials and Manufacturing Innovation, one of my very favorites. I'm on the editorial board there, and I think that they're just a rad journal. For example, we were able to publish this data set for HHI, right? So this is basically like materials abundance, price, and availability. So this is having to do with materials scarcity and availability. Who else would publish something like this? A really good, well-curated data set, and yet here we could publish it. You can actually access this data. Okay. There's other ones though we've done. We developed a benchmark AFLOW data set. So I already showed you the AFLOW library. The problem is that that library is constantly changing. So what if you're doing machine learning and that library is changing? One person does it one year, somebody else does it the same, a year later. They think that they have something that's apples and apples, but the data set has been changing. Plus, there's problems with some of these data sets. There's duplicate values. There's nonsense data that needs to be removed. So what we've done is we've created a benchmark data set. So we said at some snapshot in time, we went through and cleaned the data and said, anybody out there that wants to do this can now use this cleaned benchmark data, and you'll all get the same results. So you can test your different algorithms. We've done this with not just AFLOW, but we then followed it up and did it for a bunch of different data. So this was published. This has been accepted to the journal Data in Brief, where I'm a section editor. And we took 17, I think, different articles 17 different data sets, and we made benchmark data sets out of them. So this is my student Ashley did this. So you're seeing more and more of this. A good example of this is matbench, right? So this is out of Lawrence Berkeley National Lab. They've put together a bunch of different data sets. So here on the left, you see the names of the different data sets that they've accumulated, which have been benchmarked. And then what's really cool, it tells you not only the number of samples, but it shows you which algorithm is currently giving you the lowest error for machine learning predictions, which is pretty rad. So we'll probably come back to this a bit later and show you what are some of these killer algorithms that are doing so great right now. Okay. All right, let's say a few more words about data. Something that you'll notice as you get into materials informatics is that the crystal structure data tends to be awesome. It is so great, way better than materials property data. And that's because there are really great databases which rely on the crystallographic information file. So this was developed in, I'm sure it says here, but it was early on in the field of crystallography. They all decided, hey, let's pick one file format and stick with it, where we're all going to agree to publish. When you make a new crystal structure, when you solve a new structure, you have to report it using this exact specific file, which is machine readable, right? And as soon as you make it machine readable, that allows companies like Phys Karlsruhe, like the ICDD, like Pearson, the Crystal Impact, they can make databases where they can extract that data from the literature. You even get open source ones like the Crystallography Open database. They can extract those CIV files and they can create databases for either public or private use. The COD, for example, the public one is pretty rad. You can come in here and you can search for whatever you want. Let's search for titanium and nickel, or nitrogen like we were doing before. And we can say, I only want things that have at least 2 elements and no more than 2. So this is just going to return things with titanium and nitrogen and nothing else. Give it a moment and it crunches through its, 200,000 substructures or whatever, however many are in here. And it's going to return CIV cards for those structures. So now if you need to pull up the structure for something, there's a pretty good chance that it's here. Now the downside with the Crystallography Open database is because it's free to use, they can't pay domain experts to really check this and make sure that it's awesome and throw out things that are bad and star things that are really good, right? That stuff can be found in things like the ICSD, the Inorganic Crystal Structure Database, or the Cambridge Structure Database, or the ICDD. All of these can be curated, but you pay for it, right? They can be expensive. We use the Pearson in my group. We like the Pearson a lot. I think it's pretty great. Something else that's really great about this crystallographic information file, it allows us to generate things like CIV Checker, or Check CIV, is a tool put together by the International Union of Crystallographers, where basically you can solve a structure, create your CIV file, and then you can upload that CIV file here to Check CIV, and it will check for things that are crazy. So if you report like a bond distance that's like way too big and it's not realistic for what else is in the database, it can flag it and give it a red flag and say, hey, are you sure about this? This is really valuable because it can put guardrails on your data and prevent bad data from getting submitted to these databases, which is enormously important because bad data is going to throw off our materials informatics approaches. So really, really cool thing, which was made possible by having a standardized data format. So with that said, why don't we have this, these giant databases for all materials properties? Well, I think in large part it was because we didn't have a standardized data format for the longest time. Now that's starting to change, right? So a number of years ago, 5-6 years ago, Citrination proposed the PIF file. This is the physical information file, which was one way to sort of standardize the way that we report data so that you can now all of a sudden start making it machine readable. You can build databases that sort of interact with this in a way. 5 years later, I see that they now have GEMD, which stands for graphical expression of materials data, where they switched from the PIF to now a graph representation of materials, which is probably a better way to do it because the processes involved in material synthesis are much better represented as graphs than as the PIF. So it's evolving. I don't think that we've settled on the perfect thing, but I think we're getting closer. They say right here that this generalizes and matures the approach that was done with the PIF prior, right? So will this be the final end-all be-all? I don't know. I think it's a little bit early to say, and there's other companies and other people out there with different approaches, but these are things to be aware of. And once we do settle on something, we still have to get the community to do it, which is going to mean getting either journals to require it. That's what's happened with the CIV card in crystallography. If you try and publish something in active crystallography, they're going to say, where's the CIV? And you can't publish without it. So maybe that will happen with materials data, hopefully, eventually. Or maybe it'll be like funding agencies will say, hey, if you want to get this grant, I want to see GEMD files at the end of your research, and maybe that's what it'll take. Or maybe it'll just be the community saying, hey, we've had enough of this and we're all going to just start doing this on our own. Maybe it'll be a little bit of all of those. In any case, that's some of the landscape for materials data. Basically, it's really big. You're going to have to do some digging. You might end up in individual articles, and there's a lot of those. If you go to the journal Data in Brief, you can search and find specific articles that might have the exact curated data set for the very specific problem you want to work on. But more than likely, you're going to be taking from bits and pieces everywhere. So with that said, in our next video, we're going to actually walk through how to access some of this data from a few of these resources. We'll show you what an API is, how you might go about using it, how you might actually start to wrangle and work with some of that data. And so stay tuned for our next video.